Swayam Prabha. Digital India. Educated India.
Before we set right our this thing, what I want to talk to you is something called okay. Anyway. See, now we have talked about the devices that we can control the particulate matters, okay, or the dust. Now we want to control both. In this thing you can control both particulate matter plus gases, okay, and the system looks like this. Unfortunately I don't have the figure for this, okay. Approximate drawing, okay, and this is called Venturi scrubber. So here you pass your particulate matter and gas. For example, let's take the gas as HF, okay. This I am giving example, it can be any other gas. So this part of the Venturi is called convergence. This is called divergence, and this is called throat, okay. The challenge is, of course, the particles which are smaller in size is difficult to remove, right, okay. In here you have little openings, okay, and I'm making some drawing which may not look very good, but I think we have to be, the meaning has to be clear. You have this scrubbing solution that can be water or that can be some other chemical, okay. So what you do is that you bring the scrubber liquid and with these holes you can go a little bit inside in the depth and you can drip the liquid water or whatever is the scrubbing solution. For HF, what could be the scrubbing solution for HF if you recall? Na2CO3. You remember we talked about the wet scrubbing for the aluminum plants, right? So this could be, ordinarily it could be water or Na2CO3 depending on what you want to remove. So here you have the particulate matter and the HF. As it goes through the convergence area, it acquires very high velocity, obviously, Okay, okay, it requires a high velocity, and the particles are released. These particle water droplets will be fairly large particles, maybe 0.5 mm, 1 mm, that sort of thing. Whereas the particles that we want to remove are very fine particles, like something from 10 micron meter to about 0.5 micron meter. Smaller particles, larger particles you could remove very easily with many of the methods. So here two things happen. As this thing comes in the divergence area, okay, the velocity of these water particles or the scrubber particles will be smaller, okay, will be smaller, and the velocity of the gases, that will be faster. Okay, if you go in the convergence area, what will be happen? Then there will be relative velocity between the water droplets and the particles that are traveling. Okay, who is traveling faster? The particulate matter is traveling faster, whereas the little droplets of water is traveling slowly. When there is a relative velocity between two things, what is the result? They collide, right? When there is a relative velocity, okay, if somebody is moving at the higher speed and somebody is moving with the lower speed, thing coming from the higher speed is likely to hit that one. Okay, so what happens in this process? Okay, there is a relative velocity in this range. Okay, this relative velocity, because of this, there is an impaction of the particles onto the water droplets. Okay, and the particle will become part of the water droplet. Okay, okay. So and then many particles can go inside one water droplet. Okay, okay. So in this process, in this way, what happened? The smaller particles are encased into the larger water particles. See, and how we accomplished this? This was accomplished because we could give a relative velocity between the particles that are traveling through this one and the water droplets or the liquid, which is matter of your liking depending on what gas you want to remove. So there are two things also happening. The particles are being encased inside the water droplet, and as well as there is opportunity for the gases, which may be HF, to react with your scrubbing liquid, so that HF will be removed, because you are giving them enough time. This can be long enough. You are giving them enough time to get reaction and get so that HF is neutralized. HF is an acid. Okay, it's like acid. So that gets neutralized. Now what happens is particles, all the particles have almost have become the size of water droplets, because they are sitting inside that one. Okay. Now once the size is large, okay, it's very easy to remove. Okay. Then what we do? We provide another simple cyclone after this one. So by virtue of this, what I have done, I am not getting complicated as ESP or back filters. Okay. But here I am removing the gaseous as well as the particulate matter. But what I really need after this one is to put another particulate removal device. Okay. And that is what I want you to understand. Okay. So that we can remove the particulate as well as the gaseous sample. So this is what is called the Venturi scrubber, because this is in the shape of Venturi. Do you have anything which the physics part which you don't understand to what I said? Okay. Some material I'll send it to you through email, but just what I want is that you understand the physics. Okay. Simple thing, but then you need to understand. And as you will grow, as you will go down, there will be no more relative velocity. The particles as well as the particulate matter as well as the liquid droplets, they will travel at the same speed. So your efficiency of your collection or hitting each other will reduce with time. Okay, this is what is the thing. So this is what is the Venturi scrubber. The other thing which I have not talked to you is about SO2 removal, but you can also use the SO2 and use another liquid, like for example slurry of calcium carbonate. Okay, calcium carbonate and sulfur dioxide will react, but that part I'll send it through email. But I want to talk something. Well, hopefully if this cooperate. Normally most of the textbooks, they don't spend so much time onto this one, but in my opinion, this to understand this thing is again very, very important. If you are going to be part of an industry, okay, and working onto the air pollution and helping them to improve the air quality, you will invariably encounter with this situation. There is no doubt about that. So how do we do these stack measurements? Okay, how do we know what is the pollution that is going out? Okay. So some picture which is shown here, again this is not very clear picture, but what you see here is a little platform, okay, and then you see a person standing, right, the person who is standing, and there is little some kind of, you know, beam or bar if you like it, and something is hanging onto this bar. This can move in and out, okay, like there is a guide rail. You suppose this, like this is the weight which you see here, that can move back and forward, okay. So this is how the sampling is done, but we'll get into the physics part, okay. Why do the monitoring? Why stack sampling is required? Okay, I'll pass on this to you through email. See, suppose you are a chemical engineer. You want to see the process control. Okay, you want to see, well, the percentage of carbon dioxide should be so much. Okay, or you want to say, okay, this chemical compound is being formed or not. You are a combustion engineer. You want to see what is the oxygen level. Okay. That is why again, then you say, okay, if oxygen level is low or high, you want to increase or decrease that one, isn't it? All process control, people would like to see what is happening inside the stack or inside the duct. Regulatory compliance, you say the pollution control boards, they will come and say, oh, let me see what are your emissions, because there is a law that you cannot discharge more than certain concentration of the particles or gases and things like that. So they will require stack measurements. Air quality modeling, for modeling what you need? You need the emission quantity Q, the big Q that we were writing all the time in the formula. Where that Q will come, either it comes from the emission inventory, or if you want to be very, very accurate, you actually go and measure it, because emission inventories are always estimates. Okay, if you want to write actual, then you go and measure do thing. Development of the emission factors, okay, that emission factor you want to say, and you want to check the performance of the pollution control device. You have an ESP, for example, that we spend lots of money in there, then you want to see how good it is working. So you will say one stack measurement here, and you see one stack measurement here, and you see the difference and see how efficient is your ESP. Okay. You need to know certain basic things to do the stack sampling, that you all are aware of that one. We will not spend any time onto that one. Now I want to talk to you something you have not heard, but something very important. And all our lecture today will be focused on that particular thing. When you talk about the sampling are two things you can possibly sample: the gases and the particles, right? The gases, because of the diffusion, their concentration is uniform all across the chimney. Okay, but you will see the particle concentration will vary from location to location. Okay, that is point number one. And then, so what we do is that we sample the particulates with something called isokinetic sampling. Okay, I'll explain you what is isokinetic sampling, but before we do that, you have to answer certain thing. Suppose this is my duct or chimney. I put a sampling device to take the sample. Okay, here is my, let's say, pump, and here is my filter paper. Okay, what I do is suck through this one, take the initial weight, final weight, measure the flow. Suppose this is my velocity inside the chimney or in the duct. That is, let's say, velocity stack is Vs. Okay, and you are sucking it through some velocity, and that velocity here, okay, in this one, let me call that as Vn. Okay, okay. When Vs equals to Vn, you call it isokinetic sample, because the kinetic energy here, here and here is the same. Okay. And it is very important to maintain isokinetic sample. Okay. Now, having said it's very easy, but then you will ask why it is important. Okay. Tell me, if my Vs is greater than Vn, okay, what will happen will I collect a representative sample or I will make a mistake in sample? I will make a mistake in the sample. Okay. You are sucking with a smaller velocity. So I will report higher concentration or the lower concentration? Lower concentration. Okay. But then the question is, why lower concentration? Particles are escaping where? Particles are escaping outside or inside? If they are escaping outside, then I am collecting less. So I should report less. Is that what you are saying, that you report less or you report more? Report less. Is anyone who is with me when I say you will report higher? Why? Sampling velocity is lower. Stack velocity is higher, but you are sucking at the lower speed. The answer, what you said, is just opposite, and then you have to understand why it is so. So when you are sucking, this is your sucking velocity, right? When sucking is smaller, okay, what will happen? We'll answer with the next slide. So that is situation number 1, and then another situation is, what I am saying is, and we'll clarify, under report or over report, sorry. Over report the particulate concentration. You will under report. Generally feeling is like this, that you are sucking with a high velocity and you will expect more will come. Okay, that's what is general tendency. But this is not true, and that will become clear with the next slide, so that I don't have to make the picture again, and I will explain you in a moment. You have to think that particles have the inertia. Okay, so here, so this you see here, the velocity is the same, this here and here. Okay, now you are saying here the flow rate, okay, the sucking flow rate is lower. Okay, sucking flow rate is lower. Which is my case? This one, right? Sucking flow rate is lower. This is higher. Do you see here the same thing? What is that? My flow rate, okay, flow rate, isokinetic sampling rate is higher. Isokinetic rate is higher, okay, isokinetic rate is higher, so I am under this condition. Okay. So what will happen when you are sucking, isokinetic rate is higher? So what you do is that all the particles are sitting here. Okay. When you are sucking higher, you are able to suck the gases inside. Okay. Correct? But the particles will have its own inertia and they will continue to travel. See here, again, what is that? I have the isokinetic rate is high. So means I am sucking with the higher velocity. When I am sucking the higher velocity, all gases which is close to them, they will enter. But the particles which were there in the stream of gases, they will say, okay, gases are less inertia, they can go into the nozzle, but particle will continue to follow their trajectory. So this particle, suppose let's talk about the extreme gas, this stream. There is a particle sitting here. When you said isokinetic rate is higher, you suck in with the higher this thing. So the gas will come inside this one. Where the particle sitting here, it will continue to go like this and get escaped. Okay. Is that clear? We are oversampling because you are taking the more volume of air, but that for that volume, whatever the particle was there, that you have not captured in your filter paper. That particle, you have sampled the corresponding gas, but that corresponding particle has escaped. Okay. Is that everyone? Simple thing, but does everyone see that point? Clear? You have to be absolutely clear.
Particles which are more
Particles.
more than some certain
Particles will generally have the inertia compared to the gases. So very fine particles below 0.1 or something, that you can treat them as the gases. Maybe that problem may not be that severe. But we are in the stack, the particles can be anywhere from 150 to 1 micron. Somebody had the question.
How is it underreported?
How it is underreported? It is underreported because you have taken the gas volume, okay, but the particle mass has not come. See, if you had taken all the gas, all the particles, that was fine. Mass upon volume. So you have been able to suck the same volume, but this mass, the particle got escaped. What is the concentration? Is mass upon volume, milligram per meter cube. This mass, mass was here, that got escaped. Okay, whereas volume you have sucked through because you had the very high velocity. Okay, clear? So what will happen in this case? You will underreport. Okay, the situation is like this, for example. Okay, then you will overreport because the particles, okay, will continue to move, but the gases will escape. Okay, then you are getting more mass, but corresponding volume you are not taking. That is what is the physics that you have to understand. So very quickly, what has become most important for us is the right measurement of velocity. Okay, right measurement of the velocity and ensuring that velocity inside the chimney is same as the velocity at the nozzle. Job is done. Okay, but life is a little bit more complicated than this thing. You see, if I go and see the velocity profile in the duct, which is normally turbulent. In the duct, the flow is always turbulent for the gases. So you see the profile typically looks like this, not even parabolic what you have seen for the water and anything. For quite a distance this is 0 and then you get this one. So in that case, if I take the few points 1, 2, 3, I get the velocity profile. Okay, I need to have good knowledge of the velocity. If I make mistake about the velocity, my sampling is doomed. Okay. But unfortunately, this is a very ideal situation. We don't get that. If you go to the power plant, if you go to the chemical plant, you see the ducts are like this, then there is a fan here and the duct turns like this, okay, and then suddenly there is expansion in the duct and then again it goes like this and then again there is a turn and things like that. So unfortunately, this kind of velocity profile cannot be maintained. You see, if things are turbulent and changing and there is a cyclonic action and there may be a damper, to cut down the flow and things like that. So if I keep on taking the profiles, okay, my profile will never be like this. Only under very ideal condition. And who disturbs the profile, the velocity profile, are these things: bands, okay, expansion, contractions, ID fan, FD fans, dampers, ducts, and these things all cause your velocity profile to change. Okay. Therefore, I cannot make the measurement at just one point. Okay. This is a challenge for me, that I still get a good velocity profile. It means I should take more measurements of the velocity. Okay. In that case, I should take more measurements, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So that I get the complete profile. If I have very good picture like this, maybe I take 1, 2, 3, I am happy. Okay. But unfortunately, when you go into the field, it is never like this. And what is in the field is, that's all I will show you. This is actual measurement done by myself. Okay. And I will show you what happens there. See here, what you are seeing here is a measurement done at various time. Okay. Here you see here, velocity profile is not the perfect profile what you see. The reason why it was there, the velocity profile in 90-degree band in the upstream, there was a band which is, it was actually like this, was done in a power plant called Badarpur power station. Okay. There was a band like this, and we were having the measurements. It was a duct, horizontal duct. We were doing the measurements here. Okay. Then once you do the measurement, you see things are pushed onto this side. Okay. As a result, the velocity which should be the 0 or something was highest at this point. Okay. So suppose if I had taken only one point, I'll make terrible mistakes. Okay. So we don't want to do that. This was another situation, same plant but another chimney there. So you see the flow was just reversed. What was the problem? Spatial variation in velocity profile. Why? A 90-degree band in the downstream. Okay. And dampers, expansion and ID fan in the upstream. So there was expansion in this one. It was coming like this. Okay. And then there was expansion. and then there was a duct here, and then it followed, and we were taking the samples inside the duct. So there was expansion. Okay. Once there is expansion, the velocity increased at the ends and it was decreased less. Okay. So again, when we have said that velocity measurement is the most important or the key things, but then actual situation can make the things very difficult. Okay. So really, before going to the sample, we must determine how many data points that we want to take. Okay. And that is decided by what is at my sampling location, what is there in the downstream and what is there on the upstream. If there is things have very long duct, you have nice duct, you can do with the minimum number of samples. Okay. So if you realize, if you agree with this one, that we have to decide about the number of samples, how do we go about doing that? This is a little picture to show how do we measure the velocity. Okay, just you have to understand the principle. This is called the pitot tube. Okay, the pitot tube, one thing, this is inside the chimney. So this opening here and there is an opening here. Okay, so the gases, they will put the pressure here, the atmospheric pressure will come, and the pressure difference is nothing but velocity head. Okay, so there are certain formula corrections are there, but the underlying principle is this: you see the change in the delta H. Okay, and that is this delta H, and I can find out the velocity. Okay, just the principal part. Okay, the things may be a little different, you know, the constants are there and pitot tube constants and things like that, but this is what we call as the pitot tube, and this is called S type of pitot tube. Okay, but then the question that we are trying to answer is, how do we decide number of data points? Okay, look at this picture. Suppose I am doing the sampling here. Okay, somewhere here at distance B there is a disturbance, right, and at A there is a disturbance, there is expansion. Okay, so what you do is that you see in your, if I am going this side, my flow is like this direction is my upstream or downstream? Upstream. Okay, and when I am going this side, this is my downstream. Okay, then I see where is my disturbance, how far is my disturbance from the my sampling point. So in terms of the diameter, how many diameters I have. So suppose if my disturbance is in the upstream is, let's say, 8 times. Okay, so my disturbance is, let's say, my A, is that right? We are calling B. Okay, we call it B. In upstream. Okay, it means I am somewhere here, right? And suppose my A is 2 times in downstream. You have to see the scale up. Okay, this is 2, right? Okay, 2. I can bring it down to this 8 and 2, and you get to this point. Okay, you can see that I get to this point. This is what is my ideal situation. This is what is my ideal situation. Okay, it means if my disturbance is at a distance more than 8D, I have no problem. And if it is more than 2D in the downstream, okay, I have no problem. Then the factor which is important is 1. Multiplying factor is 1. I will explain you where this multiplying factor is to be used. Is if I extend, this is equal to 1. Okay. Suppose I have the disturbance. Suppose my disturbance is, let's say, is only distance of 6D, means I am measuring somewhere here. Okay, then this distance is only 6D. So then I go from 6 and go here and get a multiplying factor of 1.5, right? Okay. What is this, where this multiplying factor is to be used is that there is a rule that you have to have minimum number of points, velocity measurement points. So you multiply this one, suppose minimum was x. So but you have the disturbance, so you said 1.5 times x. So that many number of measurements you must take inside the chimney. Okay. What is that minimum which that you have to multiply with this factor becomes clear in this one. Depending on your internal diameter, these are the number of points, minimum number of points that are required, provided you are meeting this criteria. If you are not meeting that criteria, then multiply these minimum numbers with the factor that we got. Okay, suppose we got the 1.5 and our duct diameter was, let's say, 1.2 internal diameter. So 1.2 required 12, so we multiply this by 1.5. So 12 into 1.5 are the minimum number of points that I need to take inside the duct to do the velocity measurement. Is that clear what I said to everyone? Alright. Suppose you said, alright, let's take the example here that ID, the internal diameter was 1.2 and the factor was 1.2. So for this 1.2, minimum we required is 12 points. Okay, but unfortunately because of disturbance we got the multiplying factor as 1.5. So this becomes something like this, 18. Okay, good. So I need to take 18 points inside the chimney, so that is to ensure that I'll get a good velocity profile and I will not make mistakes. Okay, is that point clear? Now the next question automatically comes, where do I take those 18 points? Okay, there are infinite location inside the duct or inside the chimney. Okay. Then I'll show you where those 18 points can be taken. This is a little table that you have to spend little time understanding this one. Okay, I don't think you can read it so well there. Okay. This is your traverse point number. Okay, and how this is numbered is like this. This is your chimney cross section. You divide things in two parts. Okay, then suppose my point number 1, we don't know where the location is, but let me write here 1, 2, 3, 4, 5 and 6. Okay, suppose then you can say 6, 7, 8, 9, 10, 11, 12. And we always measure from the two directions. Okay, this direction and this direction. So suppose you were required to have the 12 points. So on one axis, okay, and the another axis orthogonal to this, you require 6 points. Is that right? 1, 2, 3, 6 points. Okay. So where those 6 points should come? Okay, I have taken an example for the 8 points. Okay, see here, what you have to do is suppose you are taking as, okay, you see here 8 points. This is the percentage diameter distance starting from the edge. Okay, so you have decided that you want to have the 8 data points. Okay, let's make it 8 so there is no confusion here. So you totally wanted 16 and 8 in one direction. So I can make it 1, 2, 3, 4, 5, 6, 7 and 8. Okay. So you want 8 data points. Your point number 1, here you say point number 1, total is 8, where it should be 3.3% of diameter. So my point number 1, this distance, okay, is 3.3 by 100. This distance from the inside the wall of the chimney, that is will be 3.3 percentage. I don't know if you can read somewhere, it must be a percentage somewhere. Does it say anywhere? Percent of stack diameter, okay, from inside wall of the chimney. So you can see this point is at this distance. Okay, point number 2, 10.5, my this distance 10.2 by 100 times d. So that is my this distance, right? Clear? Okay. Let's take the 8th point for example. Okay, 96.7. Okay, this is my 8th point. Then I am looking at this distance. I don't know if you can see that. Miss my 8th point from here to here. That is what is it? 96 point something. What is that? 96.7. So 96.7 by 100 times t. Clear? So you can really locate the points where you want to take the sample. Clear? And that is what I have written here exactly. Suppose you have the TP is traverse point. You need 8 number of traverse points. Look downward and locate at 3.3, 10.5 percentage dia. Clear? And this is what is again shown. And the little thing you want to be careful, sometimes we do inside the duct, okay, horizontal duct which may be rectangular, things like that. So whatever number of points you have got, okay, for example 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you divide this into that many equal parts, okay, and then you can do, and then how will you find out number of points that is required? That will be you find out the equivalent diameter DE and use the concept that A and B that I talked about for this particular diameter, okay, because this doesn't have any diameter, right, and the figure which we showed you earlier was only having the D factor. So you, for this thing you find out the equivalent diameter and then apply the same concept, number of data points required depending on the disturbances upstream and downstream, then you can locate and say okay, we need that much points. Is that clear that you can do for the rectangle? Okay. There is some special requirements are there, the diameter is there, some what should be the opening here, etc., etc. Those are more a technical thing, not that of physics part, so that you don't have to worry, but those are things, specifications are there, because here you have to put your sampling thing inside. So there should be some opening diameter and things like that, and that is given how much should be the diameter and things like that. The details are given here. This is 10 centimeter and there is a flange which you can open from the nut and bolt. Okay. This is little requirement of the stack, how you have to, the weights, the loads that will come, and then you have to provide some platform and things like that. Those details are there, those are very standard things that you can look into, but let's see where we have to understand the things. Okay, it's little opening that you see for the where you go, the sampling probe goes inside. Here you sit down with your monitors and calculators and things like that, okay, and then you find out, you have to find out the velocity on the spot, because based on that velocity only you will fix the velocity at the nozzle, right. Unless you find out the stack velocity, how will you fix the nozzle velocity? You cannot fix. So immediately you take the measurements with the pitot tube, run through the calculator or computer with the spreadsheet, and suppose you got the 20 points you have taken, and with your spreadsheet immediately will give you the velocity at 20 points. Okay. So now you know if you put your sampling probe here, what should be the velocity that you should maintain at the tip of the nozzle, right? Okay. Okay. This person, again this is not very clear to you, this person is really doing the sampling, and there is a guide rod is there, okay, and then this is a sampler which he can push back and forth. So if I want, suppose I can take the sample here, I can take the sample here, I can take the here, and normally we do take at many places to get a representative sample. Why we take the representative sample? Because the velocity is, let's say, like this, okay. Higher is the velocity, it will, because the energy is higher, it will have the larger particles, right, concentration larger particles will be more. So if I do most of the sampling here, I will still do it isokinetically, but I might lose some of the particles that are there which are the larger in diameter, okay, and I want to take a representative sample. So we don't take it, we do it isokinetically at all places, but we do it many places, okay, not at one place alone. Okay. Now how to ensure isokinetic sampling, that is a key. You have done the measurements and things like that. Now how do you ensure that, well, the Vs is equal to Vn, okay. Okay. So we have to ensure velocity in the stack is equal to velocity at the sampling nozzle, okay. And normally what we'll do, we have the measurement, we have a rotameter. To measure the flow, you want to measure the flow with what flow rate that you are measuring, because ultimately this flow rate will go in your calculation, mass divided by the volume will come from the flow rate. So we have the rotameter and there is a pump. Concept: adjust the flow rate at rotameter, okay, so that Vs equal to Vn. You know the Vs very well because you have done the measurement, okay, and now you know the diameter of this one little thing there. So you can adjust the flow rate with little knob, so to ensure that this Vs is equals to the Vn. Okay. If you can ensure that one, where do you ensure? How do you ensure? You ensure from the adjustments you make it here. Okay. If you have ensured that, means Vs equal to Vn. Any doubt? Okay. So then what I can do, I have to find out the Q that I want to adjust at the rotameter, right? That is nothing but the area of the nozzle times the velocity. That is the flow rate. This is fixed, okay. This is variable because the stack velocity may vary, okay. So this is fixed, so I multiply this and I get the flow rate Q that I can keep on adjusting here. So I have to calculate it beforehand. I take the Q, let's say 40 LPM, then I move the sampler to the second location and make it 60 LPM because velocity is different here and the nozzle is the same, okay. So you see here, I have to keep on adjusting my flow rate as I travel across the chimney, okay. Alright, life is not so simple. We haven't done the job. Concept wise we are okay, but the situation wise we are not correct. Okay, that what I state. Equation 1 is not quite right, okay, although it looks right. Why? We want Q in the stack. Where is the Q we want? In here. And but where are the measurements you are doing? In here, right? Pressure and temperature is different here, and pressure and temperatures are different here. So that Q I am maintaining, which I am measuring here, has the pressure and temperature here, which is not correct there, right? So I must make an adjustment for the pressure and temperature, which I know, which I can do the measurement of pressure and temperature here. So I must make the correction for the pressure and temperature which I am measuring, so that it becomes exactly Vs equal to Vn. So did we say that here? Can only be measured outside at the rotameter. Rotameter temperature and pressure is different than stack, so therefore we need to revise Q. Okay. How do we revise? This is fixed, okay. The volume you can revise, that volume, okay, you are measuring at Tm, so you by Tm by Ts, P1 V1 upon T1, you can see that how you will get Tm by Ts, okay, because you are here measuring at the Tm, but you want to, the required thing was at Ts. Similarly, you need to revise it for the pressure part, okay, that is the P bar, okay, that is your atmospheric pressure, minus P meter, okay, that is the difference, is you get the absolute pressure, and similarly P bar minus PS, PS is the stack pressure, okay. So that way you can, now if you maintain this particular Q at your rotameter, that will ensure that your velocity inside the chimney is same as it is in the nozzle. Okay. Is that clear to you? Okay. If it is not clear to you, I'll send this one to you, all of them. You reorganize and see if this is what it is coming out to be. Okay. You do, because if you do with your own hands, okay, you will become more happy and more clear कि yes, this is what is the thing which I have to change. Okay. There is another situation where we condense the moisture beforehand. See, stacks are likely to have the moisture, right? H2O is one of the combustion products. So in the process when you are sucking, it can condense. Okay. So if that is condensation is already removed, okay, before you are measuring at the rotometer, because the condensation, why we do is we remove the condensation, because otherwise it can spoil my rotometer, it can cause the corrosion inside the rotometer. So I want to trap the moisture beforehand. So if that moisture is removed, okay, the V meter that you have measured, okay, must be lowered, because that VV is you have already taken into the consideration. This I will send it to you through mail today, and then you have to go through this, okay, and you make sure that you are getting the same formulation as I get. If not, come back to me, okay, we can discuss and sort this one out. You become expert on the stack sampling. This is what is typically the things might look like inside. There is a nozzle here, there is a filter paper which we call as thimble, okay, and thimble looks like this, okay. This is clamped here, but this can move in and out, okay. You bring it here, you bring to the condenser, because it's the water you want to condense that one. You measure the dry gas meter, that is a flow meter that you can adjust, and there is a pressure and temperature, and this is the flow that you can measure, and finally you have the vacuum pump, so that you can make sure basically difference in the weight divided by the volume that you have taken, so that way you can find out. This is the last picture. Actually on the field it looks like this. Along with this, what you are doing is you are putting the nozzle, but you are also putting your pitot tube along with this one. Why you want to put the pitot tube along with this one? You want to ensure that velocity that you had measured earlier is still maintained in the duct. Suppose the velocity has changed, because I said with temperature, with time, velocity can change. Generally it don't. So that you can calculate at the end of the day percent isokinetic, okay, because you are doing it with some measurements which you did earlier, okay, and by the time you did your calculation, you are ready to go with this one. After 10 minutes or after 15 minutes it takes for the preparation, the velocity has changed, so that you can say how much was the change in the velocity, because you can still record the velocity because of the pitot tube. At the point only. So, but you are doing the measurement at the point only. You are doing the measurement here, okay. Then after 5 minutes of sampling, you push your sampling prop at point 2 and take the 5 minute sampling, then push to 3, again 5 minute sampling. So at that point you are re-measuring the velocity and compare it with the earlier velocity that you had measured, and say, well, you are still close to what you had measured. Suppose there is a drastic difference, it means your sampling is incorrect. Then you have to probably repeat the sampling.